Yesterday's thermal conductivity instruments typically limit characterization to a narrow range of sample materials. The samples are often forced to adapt to the instrument's rigid requirements, rather than the instrument adapting to the sample and application needs. Trident by industry leader C-Therm represents a new paradigm in thermal conductivity measurement, delivering 3 of the most powerful transient methods in one instrument. It's better to have options. Built on C-Therm's reputation for world-class thermal conductivity instruments, Trident is dynamic and satisfies the most prominent ASTM and ISO industry standards. It combines the precision of MTPS with the flexibility of TPS and the robustness of TLS, all in one modular package. These options support a wide range of applications without sacrificing ease of use. Trident meets the needs of today's labs and is future-proof for the challenges of tomorrow. The MTPS, Modified Transient Plane Source method, employs a single-sided sensor to directly measure the thermal conductivity and effusivity of materials. The method features the highest precision and sensitivity, providing accurate test results in seconds. It offers the maximum versatility for the non-destructive testing of solids, liquids, powders, and pastes. It is adaptable for high pressure, broad temperature ranges, and environmental conditions. No regression analysis is required. MTPS is the choice method for situations where reproducibility amongst multiple users matters. With a double-sided sensor available in different sizes, the Flex TPS Transient Plane Source method provides researchers the greatest flexibility over experimental parameters, including timing and power. It is recommended for more experienced users with specialty slab, anisotropy, and thin film modules available. With no contact agent required, the hot disk-style TPS sensor is ideally suited for polymers, compacted geological samples, metals, concrete, and asphalt. Flex TPS is ideal for experienced researchers looking to push the boundaries in thermal conductivity. Sheathed in stainless steel, the TLS, Transient Line Source Needle method, offers maximum robustness in thermal conductivity testing. TLS is best suited for granular materials, polymer melts, soils, slurries, and gels. C-Therm software provides full data acquisition and analysis in one user interface, allowing full control of all 3 methods: intuitive, logical, easy. Trident reflects C-Therm's years of experience working exclusively to provide labs, researchers, and manufacturers with the very best in thermal conductivity measurement. C-Therm's products are globally distributed in over 65 countries around the world, with full local support. Trident. It's better to have options.
Good day, everyone, and welcome to our webinar presentation. My name is Adam Harris, CEO for C-Therm Technologies. I'm just going to do a quick mic check with our moderator. AJ, can you just give me a thumbs up if the audio and video is coming through clearly? Awesome. Thank you very much, AJ Dow. AJ is one of our regional managers here at C-Therm Technologies and has been helping us moderate and set up these webinar. We are running a series of largely educational webinars focused on specific areas of application where thermal conductivity is of interest, trying to illuminate the importance of thermal conductivity in different applications and guide users on the appropriate method selection for different types of materials. AJ has done a great job of helping us put these together, and very appreciative for his involvement in helping us run today's event. Today's a really exciting webinar for us here at C-Therm. I've got a couple of my colleagues that are going to be joining me online. We'll have Arya Hakimian, one of our application specialists, and as well Dr. Michael Landry, who's a senior thermal scientist here at C-Therm Technologies. Today we're going to be introducing a new sensor in C-Therm's product line, a high temperature transient line source sensor. And this development is largely oriented towards application in polymer melts, but also has relevance for folks interested in geological samples where you may be looking at testing at elevated temperatures or higher pressure conditions, perhaps looking at fully saturated samples. Very applicable for enhanced oil recovery and some of those types of applications. So I'm going to jump right into this and get moving. I'm the warm-up act. Pleased to welcome you to our webinar. We are recording it, so you can share this with any colleagues. If you would like, you will automatically receive a link to the recording. Please make use of the chat box at the end of the presentation. We will offer an opportunity for some Q&A. And one of the first places we'll look is at the chat box for any questions, particularly if we're not able to address them in real time as we do the presentation. I want to just start by offering a little bit of background on who C-Therm Technologies is. I see a lot of familiar names and folks that we've worked with before, but also some newer folks that may not have that familiarity with us as an organization. We're a Canadian tech company, and our purpose, or raison d'etre in life, is very much around simplifying thermal conductivity measurement. So our goal is to make it easier to help researchers in characterizing what we describe as the materials of tomorrow. So largely focused on new types of composites, new application of new materials in novel situations. We do a lot in the electric vehicle space with thermal management, geological, all kinds of different areas. It's one of the things I love about the industry we're in, a wide range of applications we end up supporting with a very diverse set of materials. But our value proposition is all centered around driving innovation in the space of thermal conductivity. And today is a good example of that, introducing a new type of sensor, a new commercial capability, measuring thermal conductivity at elevated temperatures and pressures, as you'll see as we progress through the presentation. Just a quick overview of C-Therm's product lineup. We're not going to spend a long time on this. This is really more of an application-oriented discussion. But starting on the left of the lineup, we have our TC kit. This is our very low-cost entry level product. It's great for particularly organizations that are trying to bootstrap maybe some development, startups in the academic space where you're looking for a teaching tool or aid in running some student labs, enhance the experiential learning. This effectively gets you in the game of measuring thermal conductivity. It's paired with the Keithley source measure unit and PC, and that gives you a basic capability to measure thermal conductivity. But if what you're looking for is more of a research grade instrument for high accuracy, high sensitivity, then you're really looking at the product in the middle. That's a Trident thermal conductivity instrument. The biggest benefit to Trident is really its combination of the three most prominent transient methods for thermal conductivity. A number of those methods C-Therm has advanced or pioneered in their development, particularly the MTPS, which is the only single-sided method for measuring thermal conductivity. That gives you a lot of flexibility, for example, in thermal mapping a composite. If you're dealing with a filled material, you can often get areas where there is differences in dispersion that ultimately translate into a different thermal conductivity performance. And this can be very important in terms of understanding the performance of your overall material. The one in the middle is the transient line source or needle probe. And what you see on screen right now is our traditional one, which is rated to 200 degrees Celsius approximately. What we're going to be talking about really is the subject of focus today is a newer revision of this that's shorter, which reduces the volume of material required to run, and also offers a higher temperature and pressure range. To the left of that is the Flex TPS. I'll talk a little bit more about that in a few minutes, but it's for more advanced users. It offers some excellent capabilities in measuring anisotropic materials, thin films, really gives the user more control over the experimental parameters in terms of the test time, power, different size sensor options, etc. And we will kind of skip over the TX product in this webinar, but if you're interested in textiles or thermal touch properties, warm feel, cool touch, there is some really interesting content there, and we can direct you to some other resources that will dive deeper on the TX system. We just had a great webinar last week on the TX system, any that are interested. So throughout the presentation, you'll see reference to Trident and some of these different methods, but really we're going to focus a great deal on the transient line source method. We've branded it Needle. It's a sheathed in stainless steel. It's very robust, great for sticky situations, we like to say, particularly polymer melts where you may bond to the sensor and difficult to get off of the other types of sensors. A little bit easier with that stainless steel sheathing available with the transient line source sensor. When we talk about Trident, I like to reference this quote by Abraham Maslow. It's really about understanding that in thermal conductivity measurement, there's not a silver bullet out there. There's no one method that works well in all types of materials. They all have their benefits and their limitations, but depending on the situation, it's nice to have more of a toolbox approach, we'll say, to measuring thermal conductivity, and that's what Trident really puts forth, is a robust tool set of high sensitivity techniques, all based on transient methods, which are faster, more flexible, more sensitive for measuring thermal conductivity. This quote sums it up nicely. When all you have is a hammer, everything looks like a nail. And that's the mistake that's we see most often made in thermal conductivity measurement, is taking a good method, but applying it on the wrong type of sample. And that's when significant errors can be introduced in the measurement and then ultimately the quality of data that's produced. This slide gives you a little bit of a schematic of the different sizes and dimensions of the sensor. The traditional transient line source is 150 millimeters, so it does require larger volume of material. In the middle, we have that Flex TPS, and you can see that those are available with a range of different size sensors at 6, 13, and 30 millimeter diameter. And then the active area on the single-sided MTPS sensor is 18 millimeters, roughly the size of a US nickel coin. So it just helps inform the minimum volume requirements of these different methods. These are some of the accessories available on MTPS. I want to note the use of the high pressure cell in the upper right, and new with today's announcement, we are also launching a line of high pressure cells for our transient line source, the needle probes themselves. And that's really interesting when we talk about plastic injection molding and some of the applications in geological testing. To the left is the fluid cell. You see it with powder on the top left, and on the lower left you have the liquid version of it. Just basically remove the cap. There's an O-ring in the bottom of that cell, so it is liquid proof. To the lower right, we have the compression test accessory. This is very good for testing any kind of compressible material. If you're dealing with compressible foams, thermal interface materials, gap pads, for example, then the CTA is very important because, of course, as you compress a material, this alters in its thermal properties. What's really important is to be able to represent the application conditions for how it's applied. And we can discuss that more in detail if folks are interested in the Q&A. These are some of the accessories for the Flex TPS. So Flex TPS really gives the users more flexibility over the experimental parameters, but also the sensor is flexible. It's a nickel foil encapsulated in a polyimide dielectric material. It's sandwiched in between two samples. You see on the left the clamp that can be used. This is one of the ways to negate contact resistance Really important, particularly for higher thermal conductivity materials. Contact resistance becomes more of an influence the higher thermal conductivity range you go. This is also available, these sensors, in different temperature ranges. In the lower left, you see one of the sensors rated to 300 degrees C. There are also options up to, I think, 450, 500 degrees C as well. To the right is a powder test kit for use with the TPS option. The last point on the Flex TPS is, and it's a really important one, is there are some special utilities available with it. So these are some special functions. They're adaptations to the traditional mode of running it, which is in a bulk mode of measurement. But the slab utility allows you to test thin sheets of material. You have to input the thickness of the sample. This allows you to test a whole other type of range of materials. Works particularly well for high conductivity materials. So if you think of sheet metal and these types of applications, very good utility for that type of sample. Anisotropy, when you've got different heat transfer patterns present in a material, the through plane versus the in plane, or X versus Y direction on a sample, then really being able to distinguish that difference in thermal performance is very interesting. Almost a month ago, I think now, we hosted a nice webinar with Martin's Rubber. They're developing different rubber materials. This topic was actually on an optical repeater for submarine communication cables, where the anisotropic properties of the material were very, very important. So you'll see that highlighted in that webinar. I'll ask my colleague AJ just to drop in that link, and also where you can view other recorded webinars if any of those topics are of interest. The thin film utility is also very interesting when we're talking about polymers. A lot of formats in polymers, we're seeing more and more interest in the thin film. And there is an upcoming webinar later, I think in November, scheduled for thin film. So a couple of other interesting topic areas coming up. Okay, I want to get this transitioned over to Arya. I just want to end with a couple of quick notes. We're talking a lot about method selection as we go along here. We've highlighted 3 different methods for measuring thermal conductivity, all on one platform, Trident. Important for you to understand how to select the right method, of course. And there is an excellent resource guide available, published by C-Therm. This is a 50, 60-page resource document to help guide users in the selection of appropriate or optimal methods for measuring different types of materials. It covers steady state techniques, including guarded hot plate, heat flow meters, these types of older technologies, as well as the newer innovations in transient, including laser flash, transient techniques such as TPS, MTPS, and so forth. That link will be provided as well, and please feel free to take advantage of that free resource. I want to just end on a client testimonial. I think it's always interesting to hear from some of our clients. This is one we really like, just because of how well known the organization is, and really aligns with our feelings of trying to drive new materials of tomorrow, and contribute along that journey of innovation. And this is a nice one from NASA, just talking about purchasing a C-Therm system after seeing a demonstration of it. It provided unequivocal results and the flexibility to test powders and liquids. In terms of our satisfaction with the purchase, gave us a 10 out of 10, extremely satisfied. And that's the comments we love to hear, of course. So that's Dr. Enrique Jackson at NASA. All right, at this point, I want to pass you on to my colleague, Arya Hakimian. Arya is an application specialist with C-Therm Technologies, a thermal scientist by training, an expert in thermal conductivity measurement and related thermophysical characterization. So very pleased to pass the baton here to Arya, and I will rejoin you for the Q&A session.
Awesome, thank you, Adam. I just get my slides up on screen there for everyone. Alrighty, so just continuing on with a little bit of what Adam had mentioned, really the purpose for today's webinar is to discuss applications using the TLS surrounding polymer melts. I'll do a little bit of a background on the application, give some very simple examples, and then afterwards my colleague, Dr. Michael Landry, will walk us through some of the more advancements that have been done on the new high temperature version of the system. But just kind of, starting out, a little bit of background information. It's fairly well known that, plastic production over the past few years has significantly increased. In fact, some data has shown that within the past 20 or so years, basically more than 50% of all plastic that's been generated has been made in that time. And obviously we see the forecast there on the graph on the left projected to continually increase. Now, this production encompasses quite a wide range of sectors and different branches of industry. You kind of see packaging, construction, textiles among some of the highest. But even in electronics, these types of plastics and these applications really hit home on a lot of different areas. Now, while not all of the materials that are produced fall into one category, but there is data supporting that the majority that are developed are thermoplastic in nature. Now, a lot of these thermoplastics are produced through techniques such as injection molding, which we'll take a look at here next. So in a very basic injection molding device, you can essentially break it down into two different components. On the left there, the A side, the injection site, this encompasses where the material or the feed is loaded into. You can see the plastic granules in that top hopper. This is where the plastic feedstock gets melted down, which is again why there's the application here for polymer melts. It goes into a more of a flowable state, and then it's injected into the right side of the device. So the B side, which is the clamping portion. This will generally contain the cavity, the mold in which that plastic is injected into. And of course, this device generally has a movable component, which will pivot back and forth, allowing for different samples to be ejected and then new material to be added in, and that process can repeat. But here you can see a very simple example of that process being introduced here. Step one, obviously the material is fed through the nozzle. It's again melted down, added through those channels, goes into that molded position. In the center there, part two, that plastic is then inside that mold. So it's obviously gone from a solid to a molten state, and now it has to now re-solidify inside of that mold. And then the third aspect is the final part that you get out, which is generally ejected. And again, this process is repeated in a successive manner, really allowing for this large scale production, excuse me, for these different types of samples that can be generated. Now, there are different, somewhat related techniques. One that I'll just make mention of is a compounding process. Similar in idea here, you see that you have that extruder-based device, but what this process involves is not necessarily making a molded part or a product at the end, but it's taking different initial components, your starting materials, whether they be resins, fillers, these different additives. They go through this blending process. And then again, they go into this molten melt phase, and then they're extruded out. And then what you get is those plastic granules at the end, which is then again fed into those different molding processes. But this compounding process is generally done to improve or modify the performance of the feedstock material, whether that's to introduce a certain appearance through a dye, improve the lifespan, the modifying the chemical or the thermal properties of that sample. Again, these are just some examples of how that can be done. And of course, there are other converting methods, different other forms of production. You see some kind of images on the right. those plastic bottles, they're generally done through a blow molding technique. You can have development of spinning for fiber generation. So with those nylon spandex fibers, again, they all work off some similar idea where you have your feedstock material, and then through some device and process, your end material is in these different formats. Now, for all of these, excuse me, different methods involved, there are two really main considerations or conditions that need to be well understood. So the temperature that's introduced or maintained in the system and the pressure at which this process is subjected to. The relationship between these different aspects, the end structure, the properties of the polymer that are used, they can be rather complex. But ultimately, the way that many researchers and groups are optimizing this is through the understanding of the thermal response during the flowing and cooling state. A lot of times, these types of situations are simulated and modeled. So really being able to understand how that thermal response plays out will be very important to getting the most accurate and essentially the best product as your end result. Now, the thermal response, of course, can be really best understood through understanding the material's thermal conductivity. So we'll take a little close look at what that is and just a little bit of background there. For those who aren't familiar, thermal conductivity is essentially describing a material's ability to transfer thermal energy. See the units here, watts per meter Kelvin. You want to break that down. This is coming from the fact that there is a thermal energy or a thermal input denoted there in watts that is going to be essentially traveling through a material of given thickness across a temperature differential. Now, thermal conductivity and that heat transfer specifically in polymers, it's important to understand how that heat is conducted through these different materials. Polymers versus, perhaps metals compared to liquids, they all have different aspects that need to be considered here. But in the case of polymers, which is what we're really focusing on here today, you can essentially tie it to the fact that your conductivity of the material is highly dependent on the mean free path of the phonons that will travel throughout the material matrix. So generally, you can see that your conductivity value will increase as that mean free path decreases. So you're decreasing the distance in which that has to travel, improving the efficiency of that conduction path. So as you can see, in different types and forms of polymers, the organization of the polymer matrix is very important to describing the overall thermal properties of the sample. Again, generally better organization inside the polymer matrix will result in a decrease to that path length, and again, higher conductivity, so better heat transfer properties. So I mentioned there earlier that a lot of times this information is really critical for simulation studies. One quote here: "To accurately simulate the production conditions, heat transfer process taking place in reality must be exactly reproduced in the simulation." So it's really important to have accurate thermal conductivity data amongst other parameters for these types of studies. You can see on the table here, this was from a paper 2017 from Zink and colleagues. This data table that's presented was demonstrated to be one of the most important with respect to the inputs for their study. And we can see thermal conductivity, watts per meter Kelvin, is included there. And again, this is stemming from the fact that the heat transfer in the actual polymer itself, the components that it's interacting with, again, creates this rather complex system that you really need to have proper understanding of to ensure that the part that's generated or the device that's going to be in the output is as intended, ensuring there's no product defects or issues with that finalized part. So just to mention a few things in a very high level here, but the influence of temperature on different types of polymer materials. You can see that in general, it's been noted that A semi-crystalline structured sample will have a general net decrease before and after that transition temperature across the full temperature range, whereas materials that are more amorphous in nature, you'll see somewhat of a different trend. There's actually an initial increase in the thermal conductivity with respect to increasing temperature, again, up until that transition point. And then following that point, there's the net decrease afterwards. So different types of polymers, different types of materials will behave differently. And again, just looking at one simple example of temperature here, but also the consideration of pressure should be noted. It's generally understood that the thermal conductivity of these materials will increase with increasing pressure. Noted that inside some of those molded parts, pressures can vary, from 1,000 to 5,000 psi in some cases. So whether you're looking at something in a very low pressure state or something that's, again, with respect to temperature and pressure in combination, these can all have an influence on the resulting thermal properties of the materials that you're working with. So this brings us to really, setting up how are we doing these measurements? How are we performing thermal conductivity analysis on this really ranging material type? And again, with at C-Therm, we focus on transient classes for thermal conductivity measurements. As Adam had alluded to earlier, basically the fact that they're much faster to operate, generally more versatile with respect to the formats and the test conditions that you can use, fairly flexible on the sample size as well, really allows you to test the materials in the most representative way possible. On Trident, again, there are the three different methods that are provided, the MTPS, TPS, and TLS. But again, for us here today, the transient line source, the needle probe sensor in the middle, there's the one that's going to be mostly of interest. And again, the one that I have shown on screen here, this is just the entry-level basic TLS sensor. Again, my colleague Michael will be going a little further detail on the high temperature version here in a few minutes. At a very high level, though, your basic TLS sensor, it's completely encased in stainless steel. This makes it fairly robust and durable, really good if you're dealing with those sticky samples that may be chemically aggressive in nature, or just more challenging to work with on a different sensor type. Again, these are ideal for your viscous liquids, semi-solids, different granular type samples. Two standards that it conforms to, ASTM D5334 and D5970. The first there is with respect to geological samples. The second, more in line with different polymers and polymer melts. Now with the TLS, didn't really mention this explicitly, but it does require a little bit, I'll say, input from you as a user. You do need to ensure that the probe is calibrated properly. There is a data analysis portion to the test process that needs to be done. But again, ultimately with these transient-based measurements, you're able to perform these types of analyses within a few minutes, depending on your test conditions. So I just have one very kind of basic example here. So looking at the testing of a polymer melt, that's kind of the lower temperature range. One thing that you should always consider when using a TLS or really any measurement for thermal conductivity is anything that may be going into more of a molten or a liquid state. You need to consider the influence of convection that can occur on the samples. Generally lower viscosity materials, certain methods can introduce that convection bias, so you need to be aware of that. With the TLS, generally recommended for more viscous materials, and again, those that may be more chemically aggressive. So always good to take note of approximately the viscosity that you're dealing with, and making sure the method that is selected is done so appropriately. But here in this kind of basic data set, we show that essentially in the solid form, the material had a reference thermal conductivity noted there on the left. as it goes through that melt into more of the flowable state, we can see that kind of expected decreasing trend with increasing conductivity at again 80 and about 120 degrees Celsius. So this is, just one very basic example of how the TLS can be used. This was again the TLS, the base version on the Trident system, but at this point, what I'd like to do is introduce my colleague, Dr. Michael Landry, who will kind of take us through some applications of the new high temperature version TLS. So with that, I'll pass it along there.
Perfect. Just gonna pull up my slides. Thank you so much, Arya, for that thorough introduction. Today, I'm going to have the pleasure of talking to you a bit about some of the new R&D that's being conducted at C-Therm Technologies towards the development of a new high temperature TLS sensor. The main applications of these, obviously, are towards thermal conductivity of polymer melt materials. Now, just a little bit of background, and I'm a material scientist by training, so I love to always relate things back to materials. What is TLS mostly applicable for? For semi-solid type materials, geological samples, soils, polymer pellets, just a variety of different materials, with low viscous liquids being one as well. Today, I'm going to focus a bit more on low temperature polymer melts and how we can go from low temperature, around 180 degree melts, all the way up to 300 degree measurements. So from a polymer injection molding perspective, there are a few characteristics that are important that affect the final product of your final product out of the injection molding. Some of these include the mechanical properties of the final product. If you want something that's relatively impact resistant or is resistant to stress cracks, you're going to look at mechanical properties. Whereas selecting the final chemical resistivity and surface finish, you will select a different type of polymer. And in some of the process development side, Ari was alluding to the importance of thermal mechanical properties, the thermal expansion of the injection site, or the contraction as the mold cools the polymer to release your final product. He also alluded to the fact that thermal conductivity is super important for computational modeling of the injection process. From a process development standpoint, being able to determine thermal conductivity of the polymers that you're looking at the temperature can reduce some of the defects that are experienced during injection. So some of these defects include jetting, where cooling of the polymer or mixing of the polymer during the injection leads to streaking and undesirable characteristics. Additionally, welding type of defects where polymers are meeting together and not quite molding completely. This can lead to delamination or stress cracks, blistering, or burning of your final product, which are all undesirable characteristics. Thermal conductivity can become a proxy for you to model these types of defects and how to minimize them during a process development standpoint. Some of the common polymers that are used in injection molding are ABS, high-density polyethylene and low-density polyethylene, and nylon. And while these polymers are well characterized at room temperature, as the material becomes higher and higher in temperature during the injection molding, the thermal conductivity does decrease or increase depending on the polymer. And with polymers that are reaching towards the melting point of around 300 degrees Celsius, we need to have a method that is able to determine thermal conductivity at these higher temperatures. So a good example of this is ABS, where ABS has a strong chemical resistivity, high mechanical resilience, low melting point, and has very good desirable characteristics for injection molding. but it's not suitable for high temperature, and mold shrinkage can lead to defects in the products. And this is due to the fact that there's a poor understanding of thermal conductivity of the ABS, or additionally of additives in these polymers, which will change the thermal conductivity. Now, with the advent of adding polymer or microspheres, nanoparticles to desirably change the thermal conductivity, or to change some of the mechanical properties of polymers with the use of glass fiber and other fillers, this shifts the thermal conductivity of the final product itself, meaning that all these computational values that are completed on just the bulk polymer itself are not representative of the material that's being formulated for injected materials. So it highlights the importance of being able to measure whatever material you're going to be injecting into these molds, be it composite or bulk polymers, at the temperature and pressures of. So with that, we're going to be introducing one of the tools that C-Therm has researched and developed for being able to adapt to this challenge of high temperature and high pressure applications. So that is the TLS HT300. So with typical transient line source measurements, you have a line source that's put into your material of interest, either be a polymer melt or whatnot. And inside this actual line source is a heater wire and a thermocouple. Upon applying a specific current to your heater coil, you'll have a response and an increase in temperature locally as a transient wave going through the material. Using a thermocouple, we're able to monitor the delta T rise over log time or logarithmic time and plot the transient with respect to that. To determine thermal conductivity, it's pretty easy. You have your K value, so your thermal conductivity, it's equal to a specific calibration factor, usually 1 near room temperature, multiplied by the heat that's applied, either power per length of your probe, divided by 4 pi and the slope of the line. So in the middle of the transient, there'll be a linear region, which you can typically between around 2.3 to 4.6 long time. You'll notice a linear region, and that linear region is proportional to thermal conductivity. So increasing slope would mean a decreasing thermal conductivity, or a decreasing slope would mean an increasing thermal conductivity. So we already have some instrumentation for TLS currently available, which is the TLS 80. So what does TLS HT300 change in this respect? What it changes is the operating temperature, going from around 180 degrees Celsius all the way up to 300 and extending that range. So our total temperature range is between -55 and 300 for TLS HT300. Additionally, we have a smaller sensor size, and which leads to a smaller minimum size for your sample itself as well, leading to easier measurements during your experimentation. Not only do we have higher temperatures, but we also have the same great accuracy and precision as the TLS 80 between the two probes. And each of these are compliant with ASTM D5334 and D5930. So some of the features of the TLS HT300 are this shielded cable here. So this shielded cable allows us to achieve these higher temperatures because it's able to deflect some of the heat during the experiment. So if you have this into a larger thermal chamber, you're able to, the cable itself is shielded from these temperatures and is able to survive at these elevated temperatures. Not only do we have that, we have a 100 millimeter length probe, which is made from corrosion resistant stainless steel, which allows for easy cleaning of your polymer melt experimentation. Along with this, we have designed a series of testing accessories, including crucibles and heating block sensors or heating block heating apparatuses to allow for easy heating of samples, along with some calibration standards for high temperature measurement to ensure that your probe is working correctly. Additionally, we have designed the sensor in such a way that along with a high pressure cell, which we can provide, it's designed to withstand pressures up to 3,000 psi with the option to extend all the way up to 1,000 bar or 14,500 psi. This is super important for looking at injection molding, as the pressures in injection molding are on the same magnitude as 14,500, or between 3,000 psi and 14,500 psi. So you're able to model exactly the conditions of your polymer melt that you would experience in injection molding. The way this works is that you have your probe, which is locked in using a swage lock type fitting, along with a secondary pressure port, which allows for you to pressurize this up to those elevated pressures. This entire cell is designed to be able to fit into a well furnace, so you would have a fast and efficient heating of your polymer itself. So I was talking to you a bit about some of the precision and accuracy previously on TLS, and this same great high precision and accuracy is extended onto the TLS HT300. So we see here in these glycol replicate studies that we have a very consistent and precise measurement of glycol with a very low RSD of around 1.4 degree or 1.4%. Additionally, using some reference standards, including a CRC or a PMMA core, glycol and Maycore, we're able to achieve very accurate measurements of these thermal conductivities as compared to literature value. Now, extending this to high temperature measurement, you can use these Maycore cores to do high temperature measurements of the sample for reference. And that's what we did here in this experimentation, where we looked at the literature value of Maycore as compared to the reference value found from TLS HT300 and a different methodology, TPS, thermal conductivity measurements, as available on TRIDET. You can see that all three of these measurements at various temperatures from 25 up to 250 degrees Celsius are all consistently within 5% of the literature value, showing a very accurate method for measuring this. Now, on to some of the polymer melt data that we have. We chose to do some experimentation with ABS. Just because it's a very simple and well-characterized polymer, we wanted to show that this is working as intended. So I'm going to tell you how we are able to measure ABS polymer melts and how easy it is for us to do this. So it's easy as 1, 2, 3, meaning step 1, you would melt your ABS into a crucible to a liquid state and allow for you to insert the probe into the molten polymer and wait 15 minutes. The melting usually takes around an hour from room temperature, which is relatively quickly to melt a large amount of polymer to a molten state and be able to come to thermal equilibrium quite quickly. After that, you can set up using TRIDET software the test power and the test length that you want to do your experimentation at. After setting that up, you would press start, and you would find that your thermal conductivity values or your measurement would occur. So what we can see in this case is the delta T, or the rise in temperature compared to logarithmic time, increasing steadily, and there is a linear region that is selected between these two green bars. You can slide these green bars back and forth to find a linear region, and the feedback for that linear region is found as the R-squared value, or the regression analysis value. So once you find something that's on the order of 0.99, you know that you're in a correct region. Typically, this is between 2.3 and 4.6 for most materials. And at the end, you'll see your thermal conductivity value there. Software is very easy to use, and you're able to get multiple replicates of measurements as shown here. And what we can see in this final ABS polymer melt data is that we have a very precise and accurate measurement as compared to literature values. All the measurements are well within 5% of the literature value, showing a very robust system for measuring this sample. Now, hopefully today we are able to show you that the TLS HT300 is a very robust and accurate method for probe for measuring polymer melts, and that it's a perfect platform for testing polymer melts from -55 to 300 degrees Celsius. This, along with TPS and MTPS, offers a very complementary package for measuring a variety of different composite materials at low temperature and elevated temperature for designing and additive manufacturing applications. With that, I'd like to thank everybody that was here today. So Arya, myself, and Adam and yourself for your attention. And if you have any questions or concerns, you can reach out to us. You can contact us at info@ctherm.com or give us a call at 1-506-457-1515. I would like to also highlight some additional resources that we have available. At C-Therm.com, we have a wide variety of webinars, which you can view if you want to learn a bit more about thermal conductivity. We also have a large tech library, which is searchable by publications, which feature our instrumentation. So if you are very interested in more additive manufacturing, you can look at some of the techniques that are highlighted there and other papers. If you're wanting to take the next step, do not hesitate. We can book a video call or demo, get some complimentary testing, or you can reach out for a quote for Trident methodology. You can do so by visiting tridentthermalconductivity.com or sending an email out again. Or you can leave a quick message in the chat box and we'll get back to you very quickly. I'd like to highlight some of the upcoming webinars that we have. So the next webinar is Thursday, October 28th at 2 p.m. This is a webinar on thermal conductivity and characterization of thin films and anisotropic polymers, presented by Adam and Arya, coming up next. We have the importance of thermal conductivity in XEV thermal management modeling, which is presented with a guest speaker, Dr. Zachary Edel, with partnership at Thermal Analytics. And this is on Thursday, November 18th at 11 a.m. You can register at the website here or message us in the comment box, and we'll help you register for these upcoming webinars. And with that, I'm going to pass this back to Adam for any closing remarks before we open up the Q&A session.
Excellent. Thank you, Michael. Wonderful job, and thanks to Arya as well. At this point in the conversation, we will bring the recording to a close. So anybody that's dropping off and viewing the recording, we thank you very much for your time and attention, just echoing some of Michael's remarks. We hope you found this an interesting session. We're really excited about the new capabilities for higher temperature polymer testing. Also having some great conversation with folks on application of this particular sensor in geological sample. Very interesting for enhanced oil recovery, geothermal surveying, and characterization. So lots of interesting potential opportunity here. If you would like a quick quote, I will note that I see AJ has dropped in a number of resources. If you'd like a quick quote, there is a link there to submit. We'd certainly be happy to provide. I know it's that time of year, a lot of folks are filling in their CapEx budget requests, and sometimes it's helpful just to get some quick ballpark numbers. So there is a mechanism for us to do that. Thank you again, everyone. Delight to have you online with us today for the Q&A session. We're going to stop the recording at this point and proceed to some discussion. For anyone dropping off, have a wonderful day.